Excellent. Thank you so much. My name is Stephen Cassell. I'm a partner at ARO. This has been like a super rewarding and fun project to work on. Of course, this was a collaboration between ARO, Heintges, and also TriPyramid. Like all great collaborations, they are really rewarding, sort of rich, and also really fun. I think everyone sort of pushed the idea farther and farther forward in every meeting, and we always look forward to those weekly meetings, and of course with Andy and Andrew as well. Next, please. So we're already working with Heintges, who's a facade engineer, on a project in Brooklyn with terracotta, looking at a parallelogram terracotta baguettes. And that idea of sort of brise soleil screen sort of carried over into this project. Next, please. We're an office, ARO, who really cares about materiality, sort of the rich quality of materials, and also pattern and texture. And I think you'll see that in the project that we're going to show you. Next, please. And so early on, we knew we wanted to make a brise soleil, and really sort of talking in some of the early meetings with everybody, what we came up with is, and sort of the problem that we framed for ourselves, is to create a terracotta brise soleil that's supported on struts that span between a double layer tension net structure. And so we wanted to create this terracotta brise soleil, but we wanted to do it with a single unit. We want to sort of have we like constraints. We're an office that really likes constraints, with a single unit, and have the pattern of that unit really have sort of a rich quality of how it's experienced in light and space. So I'm going to pass it on to Leanne from ARO, who's sort of talking through the early development of the form.
Thank you, Stephen. So we started to explore the form with the abstraction of the frame. And first, we identified two ways to propagate the module: a partial grid with the checkerboard pattern and a full grid. And the depth of the frame really allowed us to test both a surface idea and a frame idea. Next, Jenny. So through these quick modeling and iterating, we were able to explore a variety of interesting patterns created by just doing a simple move on a single module. And you can see through different ways of propagation, the pattern really starts to show different porosities, which can be very dynamic. And as we keep studying, we became intrigued by this particular module, which has a V-shaped form that occupies both the front and the back of the frame. And with a very simple array, the module creates a very dynamic pattern three-dimensionally. Next, Jenny. And in researching the precedents, we are inspired by the diamond espalier found in nature, and we became interested in a similar but more abstracted idea. And the Tony Smith sculpture on the right is one example we're looking at that showed us how facets can translate that language into a geometric 3D form. Next, please. And then we started refining the details. We continued to explore the idea of using one single shape to achieve multiple design objectives. So through these few more iterations, we decided on this final form, which uses a triangular cross-section and multiple triangular facets to shape the overall module down to an elemental form. Next, Jenny. As we do this, this also brings up a challenge, as terracotta does not perform well with sharp angles. And Boston Valley has worked with us very closely to help develop the appropriate radiuses for a few weak points, while also keeping the overall geometry visually clean and sharp. And this image really shows how it looks like arrayed with the structure, and you can see the complexity starts to appear, and the pattern really shifts as you look from different angles. Next, please. And because the module has a stepped quality, we see an advantage for sun shading. As shown here, with different orientations, the module has the ability to provide sunshade for different for sunlight coming from different directions, while also keeping the views outward. And next, Jenny. To test this, we ran a few shading analysis using Grasshopper and Ladybug, both for winter and summer. And next. So first we tested a vertical surface at the facade. And on the next page, we tested a horizontal surface on the interior. And both the results showed that the module works to reduce direct solar gain in summer and also allows more light in during the winter. And the next. So we worked with Heintges closely to develop the tectonics of the module. As Bob Heintges kept reminding us to think about construction and removal of the piece, we started digging into the connection details. First, we split the one piece occupying the full grid into two identical parts. And this way, the module only has one attachment point to the frame, which results in a rotation force at the attachment. And next, please. So there are many ways we can do to counteract that rotation, but the trick here is to keep the parts identical while also be able to interlock with each other. So we created a plane splits the geometry equally and holds each other in place to balance the force. From this image, you can see how like that connection is balanced. And this zooming really shows how the two surfaces come together. And TriPyramid has provided us the neoprene path spacer in between to reduce the friction of the pieces. And again, triangle is the key shape in this detail as well. And then I'll pass to Jean from Heintges to take us through other structural developments.
Thank you, Lan. Hi, I'm Jean from Heintges. Hello, everyone. So here you're seeing some of the earlier development of terracotta connections on the screen. As Stephen mentioned from earlier on, the team is really excited about having the terracotta spanning between the depth of a minimal double-layered diagonal grid structure. And this structure is made minimal by using a lightweight, flexible tension net that's then separated by small horizontal rigid elements. So before arriving to the project connection, we studied a variety of details, some of which included attaching terracotta to the diagonal grids, as you can see on the left, as well as having grid structure being continuous through the node, is what you can see on the right. But we find that having terracotta utilize the horizontal strut for support while concealing them at the same time, being the most elegant solution. This way, so that the tiles could appear floating within the net. So the next slide shows the components in Axon at scale. So the connection is comprised of stainless steel ring profile fitting at the node, where the 1/4-inch diagonal rods starting segments are then threaded into the fitting. And there's horizontal struts, which then sleeves through the ring fitting and then through multiple terracotta pieces before it gets tightened at both ends by the spanner rods. And there are 2 bushings that are installed at the ends of terracotta sleeve to take up any tolerances between the terracotta and the rod. And this also eliminates the concentrated stresses between the two. So the photo on the bottom left shows a 1-to-1 scale of the assembled fitting that was developed and provided by TriPyramid. So the next slide shows some of the shop drawings that were developed. On the left drawing, it describes a threaded rod connection to the ring fitting. What's interesting here is that each node and each ring has a specific orientation to be constructed based on the thread direction. This is so that when you spin the rod, that will bring together the ring fitting at each ends towards each other during installation. And the detail on the right shows a strap being sleeved into the ring fitting, then tightened by a spanner bolt with the tolerances down to 1/16 of an inch being calibrated between the various materials. And then the final challenge that I will be speaking about is the unit replacement without having to disassemble the full system. We studied how each terracotta tile could be removed independently and be reinstalled. This is done first by removing the strut, which is in red. Then individual tile could be moved towards each other and rotated and eventually slid out, with the adjacent tile being supported temporarily. And the same process would work in reverse during tile installation. So Dave from my team will talk about the structure analysis for the terracotta and the building scale.
Thanks, Jean. So the first step in the analysis process was to analyze the terracotta module. So we used finite element analysis software and imported ARO's 3D geometry from Rhino to create a solid model, which ended up consisting of over 160,000 tetrahedral elements and 250,000 nodes. So fairly refined. Of course, we can't analyze the terracotta floating in space, so we introduced gravity and enough support to stabilize the element. As noted earlier, each terracotta part is supported on a stainless steel rod, which keeps it in place but doesn't prevent rotation. If we only had the rod for support, the terracotta would simply rotate downward. So fortunately, the lower leg of an adjacent terracotta element prevents this rotation, since it leans into and pushes against the base of the lower leg of our model. To account for this, we restrained our model against rotation at the base of the lower leg. We then loaded it with a fictitious 50 psf wind load, which is roughly equivalent to a 100-mile-per-hour wind speed. The analysis took about 3.5 hours, just due to the sheer number of elements, but we were able to then use those results to take a closer look at what was going on in the terracotta. So after the analysis, we studied the results, we checked the stresses at the surface and within the body of the terracotta. And during this process, we worked closely with Boston Valley to determine maximum allowable flexural stress and make sure that it was within the allowable limits. As noted here in the upper right-hand image, the maximum stresses were kind of at the interior angle of the element. This angle could be modified to reduce the stress concentration. So let's say we had a higher wind load, the greater the radius and the angle, the less intense the stress would be at that location. So that's something we could do if this were put onto a real building facade. Turning towards the lower right image, we see a more detailed study of stress planes within the solid model, enabling us to look closely at any area of interest. And on the following slide, we can see multiple interior planes reviewed for stress, which you can see here. So moving on to the tension net, we wanted to analyze the double tension net, which carries the terracotta elements. So here we took a large net structure outboard of a building facade and analyzed it. And the net is periodically attached to several floors as well as to perimeter framing. So pre-stressing the tension rods and simulating the weight of the terracotta elements enabled us to analyze the effects of wind load on the entire system. And in the next slide, you can see an exaggerated deflected shape of the same net under the maximum wind load. So one thing to note here are the points where the net is tied back at the floor slabs. There's quite a bit of angle change. So because of that increased change between one tension rod and the next, we detailed a pinned connection to accommodate the rotation without bending the rods, which you can see on the upper left-hand diagram. So now I'll turn it over to Jenny from ARO, and she'll take it from here.
Thanks, Dave. We designed a prototype building to see the module arrayed at a larger scale in tandem to Heintges' analysis. The freestanding building highlights the module deployed for all 4 cardinal directions. From the interior, views out are maintained while light is filtered through the space. The glaze is visible from the interior as well. We began developing our module for production, including discussing glazes. We chose greens inspired by the verdant and organic imagery of the diamond espalier. We had to consider how our pieces would be supported during the firing and glazing process due to their geometry. Since our modules were going to be visible from multiple angles, we wanted to maximize glaze coverage. However, all sides could not be glazed to avoid fusing to the kiln. We used this requirement to develop a support that would enhance the piece with strategic placement of the unglazed surface. The freestanding edge support was not feasible, but what we're calling the face inner saddle and outer saddle were options we considered. And you can see above in brown what would be the resultant unglazed surface of each of these. We studied how the resulting unglazed area would array across multiple modules, and we considered both front and back. In some of these cases, this is the same on both sides. But when combining options, this provided directionality. We selected the inner saddle support because we liked how its inside unglazed surface referenced the trunk of the espalier. It also worked well with our final module profile. We started from general glaze samples and narrowed it to 3, which you can see on the right. The samples were all glazed on a mocha colored clay body, which was preferred to reduce the contrast with the glazed color. And in the bottom right, you can see our final glaze, which is speckled with a tea dust that accentuates our faceted geometry. A few weeks ago, we had the opportunity to go to Buffalo to assemble our pieces. And here you can see the final jig of the inner saddle option showing the glaze on both front and back. Our module was slip cast due to the geometry. We worked with Andy Brayman at Matter Factory to identify locations for attachment points and holes needed for the slip casting and firing process. The slip cast process produces an equal wall thickness, so there is a cavity we needed to vent as seen in Dave's analysis. So that's right here. The blue rods indicate some of these different attachment points. So this one is the attachment to the net structure, and these two are showing locations for the vent holes, which we located in a concealed location. These are several of our mock-up modules, which were all identical, and you can see some of those vent holes and attachment points. And I'm going to just take you through a time lapse of our assembly. So even though the time lapse may seem like our assembly was effortless, there were still challenges. Aligning the tension net structure took some time, though paid off when it was calibrated. It also took several people to add each piece. While assembling, we were able to test out the different module configurations by solar orientation. We were excited to see that the secondary connection worked even when rotated 90 degrees. This series of photos show the facade at different angles and shows how the facade unfolds as you move in space. And here you can see details of the assembly from constructing the double layered net structure to adding the pieces in place. And this is that neoprene secondary connection as well. The secondary connections were initially drawn to have a neoprene pad support between the modules above and below it, but we realized that we could remove these and just let the modules float. We were able to take the mock-up outdoors to see how it caught light differently. It also allowed us to see it function as a brise soleil. And that is it. Thank you to everyone at ACAW and Boston Valley for this incredible opportunity. We learned so much in the development and the assembly process, and it was really gratifying to see our design fabricated with such quality and care.
Super, Jenny. Thank you so much, and thank you, ARO and Heintges for the incredible work. I had just some quick questions for you guys. One of the things that's interesting, because yours is a screen, and I think we haven't seen many of those, and it's a very elegant solution with the TriPyramid hardware detail. As you're thinking about it, obviously you have to sort of install it from both sides. And I'm just wondering how now, having done the installation, the kind of gymnastics I'm sure you've had to sort of deal with, how you're thinking about that relative to how something like this would sit against the image you show of the building and stuff.
I mean, we assume it started out actually taking 4 people to install a piece. We got it down to 3. We assume we'd get better at it later on. There would be at least an 18-inch gap there. And I think what we'd have to do is create a temporary jig, or basically to keep it from falling, that you would hook it on and help get it closer in place, so you didn't need as many hands lining it up. It took some real work to get the strut to line up with the holes. And there was a couple points where we had a rubber mallet to put it through, which honestly scared the heck out of me, but worked out fine. And so I think that honestly, that's one of the areas we'd have to also refine, is that tolerance was pretty tight. And you can imagine over a larger scale of a building, the alignment between the front and rear is going to be problematic. So I think it'd also have to have some type of jig that would hold the front and rear net in line as it was being installed, like a metal alignment system. So we roughly have an idea of it, but I wouldn't want to be the one up there on a genie lift or a scaffolding doing it myself, but I think it's possible.
And replacement of parts, it's always important. I think there's a perception that terracotta is rather brittle and stuff, and you guys were doing some pretty interesting gymnastics with it and stuff. How did you feel, having never installed it, did you feel reasonably comfortable that it could sort of handle a little bit of touching and hitting?
Definitely. I mean, we tried replacing a part. We pulled one out after we put it in, just because we were curious. We did a time lapse of that. That time lapse was not a 5-minute thing. Actually, the camera video ran out after 30 minutes. So again,
we finished right at 30 minutes. So we actually
we have a video of it. It was harder than we thought. But again, it was really the tolerance of the strut going through and the tightness of getting it in and out was the problem. It wasn't handling the piece and slipping it out. There, it was really the diameter of the hole, the strut, and because there's the piece behind it. So again, I think that's something that could get refined with further mock-ups and adjustments to the design, so it's easier.
No, it's such a lovely and elegant solution, and we really thank you for being part of ACAW this year. And yeah, look forward to including this as part of the book and sharing it widely.
Thanks for having us.
yes, thank you.
Thank you very much.